Okay, here we have question 16, and it says we've got unsaturated, and we see the double bond in the molecule, aldehydes. This is our aldehyde group here, and alcohols. Okay, so we've got 3-methyl-but-2-NL here, and apparently that's food flavouring. And we're going to react it with hydrogen bromide. So we can see we've got an alkene and hydrogen bromide, so we're going to have electrophilic addition. Alright, forming a mixture of two organic products. So that's going to be the major and the minor. Alright, so the major and the minor, according to Markovnikov's rule. So one of the organic products forms in a much greater quantity, that would be the major, than the other product. And we have to outline the mechanism. Alright, and it doesn't care whether you give the major or the minor by the looks of the question. Okay, so I'm just, to save time, going to use the molecule that's drawn out here. So hopefully you'll see this. We're going to have a Br molecule drawn like so. The bromine, of course, is going to be delta minus. The hydrogen is going to be delta positive because of the difference in electronegativity, and we're going to have a curly arrow coming from the middle of the pi bond, right, to our delta positive hydrogen, right, and then the electrons that are in the sigma bond between hydrogen and bromine are going to come off and stay with the bromine. Okay, so we've got a couple of curly arrows there. That's probably 2 of the 4 marks, and so let's draw out what we have. Okay, so we've still got our CH3 group top left, bonded to a carbon, bonded to another CH3 group here. Now we'll have one bond, that's the sigma bond that's there, and let's just draw the rest of the molecule. All right, and we've got that hydrogen that's still there. Now we've got a bond to this the hydrogen that was in hydrogen bromide. We could put it on either carbon. So let's put it on this right-hand carbon. All right, so we'll make the major product. If that's where the hydrogen goes, this carbon is now short of an electron, so we have to give it a +1 formal charge. Note, it mustn't be delta positive; it must be +1 formal charge. So that's our intermediary. That's our carbocation, and we still have our bromide ion. Okay, so it's kept both of those electrons that were in the covalent bond in hydrogen bromide. So it has a -1 formal charge. So we have that, and then the bromide ion is going to attack the positive carbon atom. So we're going to draw a curly arrow all the way around to attack that carbon that's got the positive charge. Okay, and then we can write out the final product. So we've got a methyl group, right, we've got another methyl group, and now we've got that bromine hanging off this carbon, right, and the rest of the molecule is the same as it was before, like so. So let's just read the question, make sure we've done all it's asked us to do. Outline the reaction mechanism for the formation of one of the organic products, which we have there. So I think that's good for, I think this question was 4 marks. Okay, the next part requires us to explain why one of the organic products forms in much greater quantity than the other one. And the trap here is to talk about Markovnikov's rule, which is really just a trick to get you to be able to draw the major product. It's not a chemical explanation. What they're after here is the chemical explanation, which is that the major product forms from the more stationary, the more stable carbocation. So we can write words to that effect. The major product forms from the more stable carbocation. Right, in this case, the carbocation was a tertiary carbocation, wasn't it? The carbocation of the major product was a tertiary carbocation. And there we have the 2 marks. Okay, here in part B, we have geraniol, which is an alcohol. So we've got the hydroxyl group here, and we've got citronellal, which is an aldehyde. So we've got the aldehyde group here, and they're both unsaturated. And the first thing we have to do is describe how we could distinguish between them using a test. Okay, so you could mention Tollens, right, and you'd say that you get a silver mirror with the aldehyde. Which is citronellal. So you've got that 1 mark, and then you just have to get the molecular formula of geraniol, and that's just a matter of counting up all the carbon, hydrogens and oxygens. Right, so let's do it together. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbons, and hydrogens we've got 3, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 hydrogens and 1 oxygen. Right, and they both be the same. And there you have the next mark. And sorry, my writing's going over the question here. Sorry about that. Let's explain why they're structural isomers of each other. And this is a good little sort of turn of phrase to remember, so that you're going to have the same molecular formula, right, but the different structural formula. So structural formula, when you draw the functional groups in, it's going to be different because one's an aldehyde and one's an alcohol. So the structural formula are going to be different, but the molecular formula are going to be the same. Right, now we have to explain the term stereoisomerism. Stereoisomerism, another nice sort of phrase to remember. This time they have the same structural formulae, I should say. Right, but this time the different arrangement of atoms in space, different spatial arrangement of atoms. And this is a nice question to have because it's got those 2 definitions side by side, so that you can just remember them by noticing the difference. Okay, so we've got part 5, which is about stereoisomerism, and wants us to explain the types of stereoisomerism. So straight away we think, what types are there? And so we remember we could either have EZ stereoisomerism or optical. And let's have a look at geraniol first. All right, so geraniol. And if we have a look at this double bond here, right, we can see we've got different groups coming off carbon number 3. Right, so the group coming to the bottom of carbon number 3 is different to the group above it, right? And that's the same with carbon number 2. We've got different groups coming off carbon number 2. So we're going to have EZ isomerism here, with on the left of carbon 3, this is going to be a high priority group, and on the right of carbon 2, this is going to be a high priority group. So the isomer that is drawn there in the question is an E isomer, right? So we could draw a diagram of the Z isomer. All right. So first of all, let's clarify that we've got EZ isomerism, and we should draw a Z isomer. All right. So the Z isomer we're going to draw now. So there's the two methyl groups coming off 7, and so we've got double bond there, and then got those two, right? That's carbon number 3. Still got a methyl group there. Second double bond, right? And this time we're going to draw carbon number 1 coming down below the double bond, and our OH group like so. So that would be the Z isomer. All right, so then let's go on to citronella. Let's have a look at citronella. I'll change colour. Let's do this one in green. Now, if you look at this double bond here, then this group is the same as this group, so we haven't got EZ. You could actually do a cis-trans isomer, this being a trans isomer, but I really think and I know because I've looked at the mark scheme, that what they want you to talk about is this chiral carbon. Carbon number 3 is a chiral, because we've got a methyl group and we've got two other different groups, carbons 2 and 4 coming off that carbon 3, and also a hydrogen coming off that carbon 3. So we've got 4 different groups coming off that carbon 3. So we can say we've got optical isomerism, like so, and in the same way as we did for geraniol, we should draw the other isomer. And I think the trick here is to do this like we practiced in class. Yeah, we're going to start off with our dotted line for our mirror, right? It might be, with this big molecule here, it might be an idea to like just put a dot in, away from the mirror, and another dot on the other side of the mirror, where you're going to structure the molecule around. Okay, so we want our basic framework to work on. All right, so we're going to have a tetrahedral structure, right, with a bond going into the page and a bond coming out of the page, like so. And we're going to do the mirror image of that from the other dot, like so. Yeah, and so that's our basic tetrahedral structure. And one's the mirror image of the other. So look, we're pretty good now, as long as we just add the rest of the molecule to the structure in the correct way. All right, so that's going to be like so, and that's going to be like so on the one side of our tetrahedral structure, and on the other side of the tetrahedral structure, we're just going to go like so, and we're going to do the same on the other side. And then we have two mirror images of each other that are optical isomers. Right, so you might, if you were writing this out fully in the exam, you'd make reference to your chiral center with 4 different groups hanging off your chiral carbon. Okay, and there I think we've got all the marks for that part of the question. Okay, moving on to question 17. We've got a question about amino acids. We've got the general formula of an amino acid here with our R group here, and we've got different R groups and different amino acids in this table. Okay, so first part of the question though is in the boxes which are here, draw the organic products for the reactions of serine. Okay, so we can see this is serine here. We've got our OHCH2 group here, and we can see that in serine in the question. Okay, so we've got 3 reactions to do. First of all, we're just going to acidify it. Right, so we're going to protonate anything that could accept a proton, and we see this amine group here. So the lone pair of that nitrogen is going to accept that the proton here, and we're going to get a protonated amine group. So let's draw that out. You're going to have 3 hydrogens on it. The nitrogen is going to be +1 charge, and then you just draw, that's the only thing that's going to happen, so you just draw out the rest of the molecule. Like so, and so there we have the first reaction. And in our second reaction, the top right hand one, let's have a look at what we're reacting our amino acid with, and we see we've got an alcohol because we've got a hydroxyl group here, and we've got a sulfuric acid catalyst. Right, so we think about esterification. Because we've got an acid group here that's going to react with our hydroxyl group on our alcohol with an acid catalyst to make an ester. Right, so let's draw out our ester then. So we've got our amine group, which we'll come back to at the end because we could have that protonated by the catalyst as well, but let's draw it like this for now. So we've got this part of the molecule is blissfully unchanged. Right, and we're going to draw our ester link now. So this next part of the molecule is going to come from our alcohol, and we've got a couple of CH3 groups hanging off that carbon there. So there we have it. That gets you the mark, and it also, if you had protonated this amine group with nitrogen plus and NH3 there, you would also get that same mark. And lastly, if we have a look at the reaction of excess ethanol chloride, see which functional groups that's going to react with, the functional groups in the amino acid. Okay, so is it going to react with our hydroxyl group of the acid? No, it's not, because our ethanol chloride reacts like an acid, and acids don't react with acids. Is it going to react with our hydroxyl group of this alcohol part of the molecule? Yes, it will. So it's going to make an esterification reaction with that, and it's going to react also with this basic amine group. So we're going to get a reaction there where we get the CH3CO adding on to the nitrogen, because this is going to split, and we're going to have CH3 C double bond O plus, because this chlorine is going to leave with the 2 electrons, leaving behind a +1 formal charge on our carbon. right, and that's going to be attacked by the lone pair on the nitrogen there. Okay, so we've got two reactions to do this time. Let's do the amine one first. So we've got this part of the acyl chloride molecule here. All right, and that's going to be bonded to the nitrogen, and in the process, nitrogen's lost a hydrogen, made hydrogen chloride, but we don't have to include the hydrogen chloride. And that nitrogen now is bonded to the carbon, the alpha carbon there. So we're going to just draw the rest of this bit of the molecule, which is unchanged. Right, now we come to this alcohol group, and the hydroxyl group of the alcohol there is going to react with our acyl chloride to make an ester. All right, so we're going to have our ester link there, and just going to have a CH3 on the end there, like so. So we've got our ester link being made there between the acyl chloride and the hydroxyl group, and the rest of the molecule is unchanged. So we just complete that like so, and so that would get you the remaining two of the 4 marks. Okay, let's move on to the next part of the question. Here we've got it, part 2. Right, so in part 2, we're provided with one of the 4 amino acids. Here's the 4 amino acids. We're provided with one. We don't know which one. Right, so in order to find out which one, we're going to do a titration with a standard solution of hydrochloric acid. All right, and so then we think, okay, hydrochloric acid is going to react with the amine group of the amino acid. So let's just check these amino acids and see if they've only got one amine group. Right, so we've got one amine group, no, only one amine group, because the R group hasn't got another one in it. Same with this one, same with this one, and same with this one. Right, so there's no extra complicating factor, which is a second amine group in the amino acid. Okay, so we're going to have a 1-to-1 ratio between, right, so it's 1-to-1 ratio between our hydrochloric acid and our amino group of our amino acid. Okay, so back to the titration. We've got so many grams, 5.766 grams of the amino acid in water, making up to 215 volumetric flask, okay, as usual. And then titrate this with 25 cm cubed of 0.15 molar hydrochloric acid. Okay, so because this is 25, let's put that in our conical flask. And you might not need to do this in the exam, but just in case anybody struggled with this question, let me help the understanding by drawing a little diagram. Okay, so we've decided that we're going to put our hydrochloric acid right in our conical flask, because 25 cm cubed is the usual amount we measure with a pipette. So we've got hydrochloric acid, we've got volume of 25 cm cubed, and our concentration is 0.15 mole per dm cubed. Okay, so that is in there in our conical flask, and that means we've put our amino acid. That means we've put our amino acid in the burette, and we see that we get a tetra of 21.3. So let's just put, right, let's say that's our titration. So we've got 21.3 cm cubed of our amino acid, all right, for complete neutralization, all right, and determine which amino acid. Okay, so we're going to end up working out the MR, all right. We're going to work out the MR, and the MRs of each of these are different, so hopefully the MR that we work out is going to be the MR of one of those 4, and that will identify it. So at a high level, we can look at this titration and say, well, it's easy to work out the moles of hydrochloric acid. We're going to do that first. Then we're going to refer to this molar ratio instead of our balanced equation. so that we know how many amine groups, how many moles of amino acid that will give us. And so we can use moles of amino acid. We've already got the grams of amino acid, right? And from moles of amino acid and grams of amino acid, we will get the MR. Okay, so that's the high-level plan. Let's go through it step one. And even if you can't figure out that high-level plan, all right, still start on your titration equation, your calculation, doing what you can. And the easiest thing to do is to work out moles of hydrochloric acid. So let's do that first, writing it out nicely. All right, so little n for moles of what? Of hydrochloric acid in brackets equals. So that's our concentration, 0.15. Times our volume in dm cubed, so we just go 25 over 1,000 to put it in dm cubed, and that comes out at 3.75 times 10 to the minus 3 moles. So there we have it, and so then from that we can work out the moles of amino acid, right? Because we've checked that there's only one amino group in the amino acid, right? So if it's going to react in a 1-to-1 ratio, so our moles of our amino acid in each titration right equals the same, 3.75 times 10 to the minus 3. But our moles of amino acid, I tell you what, let me just write it here instead. So in each titration, because I need the space. Okay, so our moles of amino acid, right? This time we're going to work out how much we had in the whole 250 cm cubed, right? Because that's what had that specific mass in it, right? So we have to multiply this up so that we know how much was in 250, right? So if we've got 3.75 times 10 to the minus 3 in 21.3, right, then we need to multiply that up. So it's 250 over 21.3, and that's going to give us the moles of amino acids in 250 or 5.766 grams, same thing. Okay, and that works out at 0.044. 0.044 moles, and we can put in brackets in 250 cm cubed or 5.766 grams. Right, so then we can work out, so we know we've got the moles, that corresponds to the mass of 5.766 grams, right? So straightforwardly we can work out the MR, which is mass over moles. All right, so the mass is our 5.766, moles is our 0.044. All right, so that leads to an MR of 131. All right, grams per mole. All right, and then you just check that versus the MR of those amino acids, and you'd find out that the amino acid concerned is leucine. Okay, here we have part B, and we're now onto chromatography, and we're provided with another of the amino acids, which we have to identify this time using chromatography. All right, so we've been given 2 chromatograms, here they are, of the amino acid, and they're in different solvents, W and X. Okay, so looking at the question, first question is what is the RF value of serine in solvent W? Okay, so here's solvent W, and here's serine, and RF values we know are this distance divided by this distance, right? So get your rulers out, measure those two distances, do the division, and the answer comes out to be between 0.33 and 0.35. If you get a number between those two, you get that mark. Okay, we move on to part 2 now, and we've got to identify the unknown amino acid. All right, so here's our unknown amino acid in solvent W. All right, so and here's our dot, which matches leucine and glycine. All right, so it matches leucine and glycine in solvent W. All right, but in solvent X, here it is, and it matches this time alanine and glycine. Okay, so glycine is the common factor in the two chromatograms. So glycine is our answer. All right, and the explanation would be, all right, our unknown amino acid matches leucine and glycine in W, right, and it matches alanine and glycine in X, right, and that gets you that second mark.